What if I told you that everything you think you know about the asteroid belt is wrong? It's not a deadly obstacle course of colliding rocks. It's not a dense wall of debris. In fact, if you stood on an asteroid in the heart of the belt, you probably wouldn't see another asteroid with your naked eye. The nearest neighbor might be millions of miles away, invisible in the darkness. Yet scattered across this profound emptiness are time capsules from the birth of our solar system, ancient ocean worlds still harboring liquid water, and pristine samples containing the chemical building blocks of life itself. For the next hour, we'll drift together through this misunderstood realm and discover why this graveyard of a planet that never formed holds the secrets to understanding where we came from. Picture yourself standing on a dark, cratered asteroid tumbling slowly through space. You're somewhere between Mars and Jupiter, in the heart of what we call the asteroid belt. Now look around. What do you see? In movies, you'd be surrounded by a chaotic storm of rocks, dodging collisions every few seconds. But the reality would leave you breathless for an entirely different reason. You would see nothing. Absolute, profound darkness punctuated only by distant stars. The nearest asteroid large enough to make out with your eyes. Probably several million kilometers away. Too far, too dim, too small to detect. This is the first truth about the asteroid belt. It is almost entirely empty space, a cosmic desert where loneliness stretches across billions of cubic miles. The asteroid belt spans a region from about 205 million miles to 307 million miles from the Sun. This creates an enormous ring-shaped zone, a torus of space that's over 140 million miles across and stretches vertically for tens of millions of miles. Now here's what makes this remarkable. All the asteroids combined, every single rock, boulder, and dwarf planet in this vast region, contain less mass than 4% of our Moon. Imagine taking our Moon, keeping only a tiny fraction of it, and scattering those remnants across a space so vast that you could fit trillions of moons inside. That's the asteroid belt. Not crowded, not dense, profoundly, almost incomprehensibly empty. To truly grasp the scale, let's shrink the solar system down. Imagine the Sun is the size of a softball sitting in front of you. At this scale, Earth would be a tiny grain of sand about 26 feet away. The inner edge of the asteroid belt would begin 76 feet from you, the outer edge at 113 feet. Now here's the astonishing part. All the asteroids combined would equal about half the thickness of a standard wire in a paperclip. Take that tiny amount of wire, break it into millions of microscopic fragments, and scatter them randomly across that 37-foot wide disk. Walk through it, and you'd likely never encounter a single piece. This is the scale we're dealing with, a scale that defies intuition. NASA learned this truth the hard way, or rather, the easy way. When Pioneer 10 became the first spacecraft to cross the asteroid belt in 1972, mission controllers held their breath. Did it survive? Would it collide with debris? Would micrometeorite impacts cripple the probe? The answer shocked many. Pioneer 10 detected only a few impacts from micrometer-sized particles during the entire crossing. Since then, over 15 spacecraft have traversed the belt without incident. Voyager 1 and 2, Galileo, Cassini, New Horizons, Dawn, Lucy, Psyche, all passed through as if crossing empty space, because that's essentially what they were doing. Engineers don't even bother calculating trajectories to avoid asteroids. In fact, if they want to visit one, they must deliberately alter course to intercept it. Scientists have calculated the actual collision risk. If you sent a spacecraft through the asteroid belt without any course planning whatsoever, what are the odds it would accidentally hit an asteroid? Less than 1 in a billion. You're more likely to be struck by lightning multiple times in your life than a random spacecraft is to collide with an asteroid. This statistical reality demolishes decades of science fiction imagery. There are no harrowing chases through dense debris fields, no piloting skills required to dodge tumbling rocks. The belt is so empty that collisions between asteroids themselves occur once every few 100 million to several billion years for any given object. When you're waiting hundreds of millions of years between traffic accidents, you know you're in a very empty place. The average distance between asteroids in the main belt? About 600,000 miles. That's the equivalent of laying 24 Earths end to end, rim to rim, then placing asteroids at each end. Even in the densest regions of the belt, you'd still be looking at separations of hundreds of thousands of miles. If you could somehow gather all the asteroids and pack them into a single sphere, that sphere would measure only about 1,500 kilometers across, smaller than our moon, which itself is barely 1/4 Earth's diameter. We're not talking about the remnants of a destroyed planet here. We're talking about a planet that never had the chance to form, its building materials scattered before they could ever come together. Think about what this means. The asteroid belt has been portrayed as the universe's most dangerous shooting gallery, a place where only the most skilled pilots dare venture. Yet the reality is the exact opposite. It's one of the safest regions to traverse in the entire solar system. But here's what makes it truly precious. Because collisions are so rare, because the asteroids are so isolated, because they've drifted undisturbed for billions of years, they've preserved the solar system's original materials in near pristine condition. This emptiness isn't a flaw or a disappointment. It's exactly what makes the asteroid belt invaluable. In a cosmic graveyard where nothing collides, where nothing erodes, where nothing changes, the dead speak to us clearly across the eons. Temperature in the belt varies with distance from the sun. At the inner boundary, surface temperatures reach about -73 degrees Celsius during the day, while the outer regions cool to -108 degrees. These are frozen, dead worlds where water exists only as ice harder than rock, where any atmosphere would have escaped into space billions of years ago. But don't mistake cold for uninteresting. At these temperatures, volatile materials that would evaporate on warmer bodies remain locked in place. Organic molecules that would break down under intense sunlight stay preserved. Ancient ices that recorded the composition of the early solar system remain unchanged. The cold isn't a curse, it's a blessing, a natural freezer that has kept 4.6 billion years of history fresh and readable. Not all asteroids are created equal. If you could visit a dozen randomly selected asteroids, you'd encounter an astonishing variety of worlds. Some would appear almost black as coal, absorbing nearly all the sunlight that touches them. Others would gleam with a stony brightness, reflecting light like desert rocks under a harsh sun. A few might even show the dull metallic sheen of iron and nickel, the exposed hearts of worlds that never finished forming. This diversity isn't random. It tells the story of where in the solar system each asteroid was born and what it experienced in those first few million years after the sun ignited. The asteroid belt isn't a single population of similar objects. It's a museum displaying samples from across the entire infant solar system. 3 primary types dominate the belt's population. C-type asteroids, the carbonaceous class, make up about 75% of all asteroids. These are the darkest objects in the solar system, with surfaces blacker than charcoal, reflecting less than 10% of the light that hits them. Imagine holding a piece of coal in your hand. Now imagine that coal has been sitting in space, unchanged, for 4.5 billion years. That's a C-type asteroid. They're loaded with carbon compounds, hydrated minerals, and organic molecules. These are the most primitive materials we know, ingredients that predate the planets themselves, survivors from the solar system's very first moments. Looking at a C-type asteroid is like looking at the original recipe from which everything else was made. S-type asteroids, The silicaceous or stony asteroids comprise about 17% of the population. These look more like terrestrial rocks, with a grayish or reddish-brown appearance and significantly higher reflectivity. Unlike their carbonaceous cousins, S-types have been cooked. In the first few million years after they formed, short-lived radioactive elements heated them intensely. Some melted, partially or completely, allowing heavy metals to sink toward their centers while lighter silicates floated to their surfaces. The minerals you see on an S-type asteroid, olivine, pyroxene, metallic flecks, are the products of thermal processing, proof that these bodies experienced volcanic-like activity billions of years ago. They're not pristine, they're transformed. And that transformation tells us about the intense heat and violence of the early solar system. Then there are the M-types, the metallic asteroids making up roughly 8% of the belt. These are the strangest of all. Composed primarily of nickel-iron metal, they likely represent the exposed cores of shattered protoplanets. Imagine a world forming, growing large enough that its interior melts and differentiates, heavy metals sinking to create a core, lighter rocks forming a mantle. Now imagine a catastrophic collision that blasts away all the rocky exterior, leaving only the metallic heart exposed to space. That's an M-type asteroid, planetary viscera laid bare, organs without a body. Some M-types may contain nickel-iron concentrations of 85% iron and 10% nickel. If you could somehow transport one to Earth, setting aside the impossibility, a single metallic asteroid might contain more metal than humanity has mined in our entire history. This compositional diversity reveals the ancient temperature gradient of the protoplanetary disk. C-types dominate the outer belt, around 3.5 astronomical units from the Sun. At these distances, temperatures were cold enough for water ice and organic materials to condense and survive. Closer in, at about 2 astronomical units, S-types dominate. Here it was. Warmer water existed only in hydrated minerals, and thermal processing was more intense. This gradient is a frozen snapshot of conditions 4.6 billion years ago. By mapping where different asteroid types live today, we're reading the temperature zones of a disk of gas and dust that vanished more than 4 billion years ago. We're seeing through time, reading history written in the distribution of rock types across empty space. Size diversity is equally dramatic. The smallest officially tracked asteroids measure just 2 meters across, about the size of a small car. These tiny worlds tumble through space, barely more than boulders, yet each has its own independent orbit, its own cosmic destiny. At the other extreme, the largest asteroid, Ceres, spans nearly 1,000 kilometers, large enough to pull itself into a sphere through its own gravity. Between these extremes lie over 1 million asteroids larger than 1 kilometer, and perhaps billions of smaller fragments. But here's a startling fact: the 4 largest objects, Ceres, Vesta, Pallas, and Hygiea, contain about 62% of the belt's total mass. Everything else, the other million-plus asteroids, share the remaining 38%. The belt isn't democratically distributed. It's dominated by a few massive survivors. Shape tells its own story. Most asteroids are irregular, potato-shaped, lumpy, misshapen. Only the largest have enough gravity to pull themselves into spheres. But recent spacecraft visits have revealed fascinating exceptions. Some asteroids are spinning so fast, approaching a rotation period of about 3 hours, that centrifugal force has deformed them into diamond shapes or spinning tops, with prominent equatorial bulges where material has migrated outward. Others are rubble piles, loose collections of fragments held together only by weak gravity, more like flying gravel pits than solid rocks. Some asteroids have been shattered and reassembled multiple times, creating internal structures like broken pottery glued back together. Each shape is a biography written in form, a record of impacts, rotations, and gravitational interactions stretching across billions of years. Some asteroids don't even travel alone. Binary and multiple asteroid systems have been discovered, where one asteroid orbits another, or where an asteroid has captured smaller moons. In 2024, the Gaia spacecraft identified 352 potential new binary asteroids by detecting the subtle wobble caused by an unseen companion's gravity. This suggests that roughly 1/6 of all asteroids may have companions, silent partners orbiting in the darkness, invisible except through careful measurement. Why do asteroids have moons? Sometimes from collisions that eject material into orbit, sometimes from close encounters that allow one asteroid to capture another. Each binary system is a miniature solar system, a small family drifting together through the cosmic void, bound by gravity's gentle embrace. Among the millions of asteroids, 4 stand out as giants. We'll explore each in turn, beginning with Vesta, a world that almost became a planet. At 525 kilometers in diameter, Vesta is the second largest asteroid in the belt. But size alone doesn't make Vesta special. What makes it extraordinary is what happened inside this world during the solar system's first few million years. While most asteroids remained cold, inert piles of rock, Vesta melted. It differentiated. It developed an iron-nickel core, a rocky mantle, and a basaltic crust. In every meaningful sense except size, Vesta became a planet. It's a survivor from an era when hundreds of such protoplanets were forming, most of which were destroyed or ejected. Vesta endured, and in doing so became a window into planetary birth. What heated Vesta enough to melt it? Short-lived radioactive isotopes, particularly aluminum-26 and iron-60. These elements existed in the early solar system but decay rapidly, with half-lives measured in hundreds of thousands or millions of years. When Vesta formed from the collision and sticking of countless smaller bodies, these radioactive elements became concentrated in its interior. As they decayed, they released heat, enormous amounts of heat. Within just 1 to 2 million years after formation, Vesta's interior reached temperatures high enough to melt metal and rock. The heavy iron and nickel sank toward the center, forming a core about 220 kilometers in diameter. Lighter silicates floated upward, creating a mantle. The surface, basaltic lava flows created a crust. Vesta became a miniature Earth. NASA's Dawn spacecraft orbited Vesta from July 2011 to September 2012, mapping every crater, every cliff, every ancient lava flow. What? The mission revealed stunned scientists. Vesta's surface is dominated by catastrophic violence. The South Pole bears an enormous scar called Rubble, an impact crater spanning 500 kilometers, 95% of Vesta's entire diameter. This wasn't a glancing blow. This was an impact so powerful it excavated material from deep within Vesta's interior, blasting roughly 1% of the asteroid's total mass into space. The collision would have generated seismic shockwaves that propagated around the entire body, cracking and fracturing the crust. It's remarkable that Vesta survived at all. A slightly more powerful impact might have shattered the asteroid completely. The Rubble impact created a central peak mountain that rises 22 kilometers above the crater floor, making it one of the tallest mountains in the entire solar system, nearly 3 times the height of Mount Everest. Imagine standing at the base of this cliff and looking up. The summit would extend beyond the horizon, disappearing into the black sky. The mountain wasn't built by volcanic forces or tectonic uplift. It rebounded upward in the instant after impact, like dropping a stone into thick mud and watching a central splash freeze in place. This mountain is frozen violence, a monument to the collision that nearly destroyed Vesta. And because there's no erosion, no weather, no wind or rain, the mountain stands exactly as it did when it formed, perhaps 1 billion years ago. That ancient impact did something else remarkable. It scattered fragments of Vesta across the solar system. Some of those fragments eventually fell to Earth as meteorites. Scientists had been studying a particular class of meteorites for decades, the HED meteorites, named for their three subgroups, Howardites, Eucrites, and Diogenites. These meteorites showed clear evidence of having come from a differentiated body, a world that had melted and formed distinct layers. But where was their parent body? Dawn solved the mystery. The composition of HED meteorites matches Vesta's surface perfectly. We have pieces of Vesta in our museums, in our laboratories, in our hands. We've been studying this asteroid for decades without knowing it, touching fragments of a world we'd never visited. Vesta rotates rapidly, completing one full turn in just over 4 hours. If you stood on its surface, you'd experience a day-night cycle where the sun would race across the sky from horizon to horizon in the span of a few hours. With an axial tilt of 29 degrees, similar to Earth's 23.5 degrees, Vesta even experiences seasons as it orbits the sun. But these aren't temperate seasons. This is a world where summer might reach minus 30 degrees Celsius and winter plunges to minus 200 degrees. There's no air, no water, no protection from the sun's radiation or the eternal cold of space. Yet Vesta has weather of a sort. Temperature changes cause thermal stress in the rocks, cracking them gradually over billions of years, creating a layer of broken regolith covering the surface. Dawn's cameras revealed another mystery: enormous troughs, canyons that dwarf Earth's Grand Canyon, carved into Vesta's equatorial regions. One system, called Divalia Fossa, stretches hundreds of kilometers and plunges several kilometers deep. How did these form? The prevailing theory suggests they're fractures caused by the Resilvia impact. When that massive collision occurred, shock waves propagated through Vesta's interior and around its surface. The stress was so intense that the crust cracked, creating these enormous rifts. They're frozen echoes of violence, scars that will remain until the end of time. There's no tectonic activity to seal them, no erosion to soften them. They exist now exactly as they did when they formed, a permanent record of the day Vesta nearly died. Vesta occasionally becomes bright enough to see with the naked eye from Earth, the only asteroid regularly visible without a telescope. On particularly favorable oppositions, when Vesta is closest to Earth and fully illuminated by the sun, it reaches magnitude 5.2, just barely visible to the unaided eye under dark skies. For a moment, you can see with your own eyes a world 200 million miles away, a protoplanet that experienced the birth of its core, the eruption of basaltic lavas, and catastrophic collisions that should have destroyed it. That faint point of light carries all that history compressed into a single photon reaching your retina. Vesta reminds us that even in emptiness, even in silence, there is profound story. While Vesta formed properly and differentiated into a miniature planet, its siblings followed different paths. Pallas, the third largest asteroid at 512 kilometers diameter, never achieved true planetary form. It remains elongated, irregular, decidedly non-spherical. Wrong. Perhaps nothing went wrong at all. Pallas may simply represent a different evolutionary path, a world that accumulated more slowly, that never heated enough to melt and reshape itself, that was assembled from colder materials farther from the sun. Perhaps Pallas experienced its own catastrophic impact early on, one powerful enough to deform it permanently. Either way, Pallas stands as a counterpoint to Vesta. Not every large asteroid became a protoplanet. Some remained primitive aggregations, barely changed since they first formed. What makes Pallas truly extraordinary is its orbit. Most asteroids orbit in roughly the same plane, the ecliptic, the flat disk in which the planets move. But Pallas's orbit is inclined at 34.8 degrees to this plane. Imagine a highway where all the cars travel in orderly lanes, then one vehicle suddenly decides to drive at a steep diagonal, crossing through traffic rather than following the flow. Oh, that's Pallas. This high inclination makes the asteroid incredibly difficult to reach with spacecraft. The amount of energy required to match Pallas's tilted orbit is prohibitive, which is why, despite being the third largest asteroid, it remains unvisited by any probe. Pallas keeps its secrets close, inaccessible, protected by the simple tyranny of orbital mechanics. Evidence suggests Pallas experienced a catastrophic impact at its south pole, one that excavated roughly 6% of the asteroid's entire volume, twice as much material as was blasted from Vesta by the Resilvia impact. This collision may have done more than crater Pallas. It may have fundamentally altered its rotation and orbital properties. The impact could have increased Pallas's orbital inclination, sending it on its current tilted path. It certainly slowed the asteroid's rotation. Today, Pallas spins once every 7.8 hours, relatively leisurely for an asteroid of its size. The impact scar remains visible as a huge depression in the southern hemisphere, a wound that will never heal because there is no process to heal it. On Pallas, violence becomes permanent geography. Compositionally, Pallas resembles carbonaceous, chondrite meteorites, primitive materials rich in water-bearing minerals and organic compounds. Unlike Vesta, which heated extensively and lost most of its volatile materials, Pallas likely never exceeded about 820 Kelvin in temperature. This means its water remained locked in hydrated silicate minerals rather than being driven off as steam. The interior is probably homogeneous, no core, no mantle, no crust. Just a relatively uniform mixture of rock, metal, and hydrated minerals extending from surface to center. Pallas is what Vesta might have been if it had never melted, a primitive accumulation, a pile of solar system building blocks barely modified since assembly. It's less evolved, certainly, but in its primitiveness lies scientific value. Despite its size, Pallas appears remarkably dim from Earth. Its dark, carbonaceous surface reflects very little light, giving it an apparent magnitude of around 8.0 under typical conditions, well below naked eye visibility. During rare perihelic oppositions, when Pallas is simultaneously closest to both Earth and the Sun, it can briefly brighten to magnitude 6.4, just barely approaching the threshold of human vision under perfect dark skies. But these favorable alignments occur only once every several decades. Most of the time, Pallas remains invisible without a telescope, a massive world hidden not by distance alone but by its own light-absorbing surface. It's the asteroid equivalent of stealth, present but undetectable, massive but invisible. Now, turn your attention to Hygiea, the fourth largest asteroid and perhaps one of the most mysterious. Recent observations suggest Hygiea may actually be nearly spherical, with dimensions of 450 by 430 by 424 kilometers, making it the second most spherical object in the asteroid belt after Ceres. If confirmed, this would mean Hygiea meets the criteria for hydrostatic equilibrium. It has enough mass that its own gravity has pulled it into a round shape. Under International Astronomical Union definitions, this could make Hygiea the fifth dwarf planet in our solar system. But here's the puzzle. How did Hygiea become spherical? Unlike Ceres, which clearly melted and differentiated, Hygiea shows no evidence of such extreme heating. Its spherical shape has a different, more violent origin. The answer, scientists believe, lies in complete catastrophic disruption. At some point in its past, Hygiea was struck so violently that the entire asteroid shattered, not just cratered, but completely broken apart into countless fragments. For a brief period, there was no Hygiea, only a cloud of debris expanding into space. But gravity is patient and persistent. Slowly, over perhaps 4 hours, the fragments fell back together, reaccumulating into a single body. As they reassembled, the debris behaved almost like a fluid, oscillating, rearranging, settling under gravity's influence into the lowest energy configuration, a sphere. Then the motion stopped. The fragments locked together, and Hygiea became solid again. But now with no memory of its previous shape, no surviving surface features from before the catastrophe. The collision erased Hygeia's history and rewrote its form. This history explains why Hygeia's surface appears relatively smooth and lacks the large impact craters that should exist on a body this old. When the asteroid reassembled, it created a fresh surface, erasing all previous craters. Any impacts since that reassembly occurred would have created new craters, but Hygiea has been fortunate or isolated enough to avoid major collisions in the time since. The asteroid did spawn a family of smaller bodies, fragments that escaped during the disruption and never fell back. These Hygiea family members orbit nearby, silent witnesses to their parent body's death and rebirth. Like Vesta, Pallas, and Ceres, Hygiea tells a story of violence written in form and orbit. In the asteroid belt, catastrophe is the primary author of geography. If the asteroid belt has a king, it is Ceres. At 939 kilometers in diameter, Ceres dominates the belt, containing between 25 and 40% of its entire mass, more than all other asteroids combined save the top 3. Ceres is large enough that gravity has pulled it into a nearly perfect sphere, earning it classification as a dwarf planet in 2006. But size alone doesn't make Ceres remarkable. What makes this world extraordinary is what lies beneath its surface, an ocean. Not an ancient, long-frozen ocean that existed billions of years ago. Recent evidence suggests liquid water exists under Ceres' surface right now, today, making this distant world an active ocean world without the tidal heating that powers similar activity on moons like Europa and Enceladus. Ceres spins rapidly, completing one rotation in just 9 hours, a fast day even by asteroid standards. With a nearly zero axial tilt of only 4 degrees, Ceres experiences virtually no seasons. Its orbit takes 4.6 Earth years to complete, tracing a path around the Sun at an average distance of 257 million miles. Surface temperatures are brutally cold, -28 to -136 degrees Fahrenheit during the day, plummeting to -225 degrees at night. These are the temperatures of the outer solar system, where water exists only as ice harder than steel. Yet despite this cold beneath the surface, Ceres harbors warmth, liquid, and perhaps the final remnants of an ancient global ocean that once existed beneath the crust. The interior structure reveals a partially differentiated world, organized into 3 distinct layers. At the center lies a rocky core, about 400 kilometers in radius, with a density between 2.5 and 2.9 grams per cubic centimeter. This core likely contains primordial chondrules, millimeter-sized spheres of once molten rock that formed in the protoplanetary disk and never fully remelted. Above the core extends a thick mantle, 70 to 190 kilometers deep, dominated by hydrated rocks and clay minerals with a density of about 1.7 grams per cubic centimeter. Finally, the outer shell, a crust roughly 40 kilometers thick, mixing ice, salts, and hydrated minerals at a density of only 1.25 grams per cubic centimeter. This crust is less dense than water, a shell of ice and rock floating atop denser material below. Approximately 25% of Ceres' mass consists of water ice, potentially 200 million cubic kilometers of water. To put that in perspective, that's more fresh water than exists in all of Earth's surface, lakes, rivers, and ice caps combined. Ceres is the most water-rich body in the inner solar system after Earth itself. When Ceres formed 4.6 billion years ago, it accreted substantial ice from the outer solar system. As radioactive elements in the core decayed, they released heat. The ice melted, separating from rock and forming a subsurface ocean. For perhaps 1 billion years or more, Ceres was a complete ocean world, a rocky core surrounded by a shell of liquid water several kilometers deep, topped by an ice crust. That ocean has now largely frozen. But pockets remain. Before NASA's Dawn spacecraft arrived, astronomers had observed bright spots on Ceres' surface, mysterious features that reflected far more light than the surrounding terrain. What were they? Least deposits, smaced salts, geysers. When Dawn entered orbit in March 2015, the answer proved more complex than anyone expected. The bright spots are sodium carbonate salt deposits, highly unusual for the solar system. The largest concentration lies in Okator crater, 92 kilometers wide and 4 kilometers deep. Within Okator are two main bright regions, Cerealia facula, a central dome, and Venalia faculae, scattered deposits to the east. These features shine with 40% reflectivity, 4 times brighter than the surrounding dark surface. They're salt plains left behind when subsurface brine reached the surface and evaporated. Here's what makes the bright spots astonishing. They're young. The salt deposits are less than 2 million years old, geologically instantaneous on a world 4.6 billion years old. Some areas contain hydrated salts that should dehydrate and darken within hundreds of years under Ceres' surface conditions. Yet Dawn's instruments confirmed these salts still contain water molecules. The implication is inescapable. Fluids reached the surface very recently, perhaps within the past few years or decades, possibly continuing even now. Okator crater formed about 20 million years ago when an impact blasted through Ceres' crust. That impact created fractures extending deep into the interior, connecting the surface to a subsurface brine reservoir. Slowly, over millions of years, salty water has percolated upward through these cracks, occasionally reaching the surface and evaporating, leaving behind ever-accumulating salt deposits. Beneath Okator lies a deep reservoir of concentrated brine, extending hundreds of miles wide at a depth of about 40 kilometers. This represents what remains of Ceres' ancient global ocean. As that ocean froze from the top down over billions of years, salts became increasingly concentrated in the remaining liquid, lowering the freezing point. The result is a layer of extremely salty water, perhaps 30% salt or more, that remains liquid even at Ceres' cold internal temperatures. Gravity measurements confirm this liquid layer's existence. Chemical models predict its composition, primarily water mixed with sodium carbonate, ammonium chloride, and possibly magnesium sulfate. This is alien water, far saltier than Earth's Dead Sea, existing in darkness under miles of ice. Yet it is liquid water, and where there's liquid water, there may be chemistry, complexity, perhaps even simple life. Ceres practices a form of volcanism unlike anything on Earth. Instead of molten rock, Ceres erupts with cryomagma, a slushy mixture of water, ice, salts, and volatiles. Scientists have identified 22 to 30 cryovolcanoes scattered across the surface, with a new one forming roughly every 50 million years. The most prominent is Ahuna Mons, rising 4 kilometers above the surrounding terrain, with a base spanning 17 kilometers. This pyramidal mountain formed through effusive eruptions where cryomagma oozed from below rather than exploding violently. Ahuna Mons is young. "200 to 240 million years old and still retains its original shape. But other, older cryovolcanoes have undergone viscous relaxation. They've slowly flattened over hundreds of millions of years like cold honey gradually spreading. These relaxed domes appear as gentle swells in the terrain, ghosts of ancient mountains that time has smoothed. In 2017, Dawn made a discovery that transformed our understanding of Ceres and the asteroid belt. Near Untouchable crater in the northern hemisphere, the spacecraft detected organic materials, carbon-based molecules that form the basis of life as we know it. These aliphatic hydrocarbons, chain-like organic molecules, appeared as scattered deposits with a characteristic spectral signature. Their presence raised immediate questions. Did these organics form on Ceres itself through internal chemical processes? Or were they delivered from space by impacting asteroids from the organic-rich outer belt? A January 2025 study using artificial intelligence to analyze the entire Ceres surface concluded that organics are rare, mainly concentrated around Untouchable, with only 2 other small patches discovered. The evidence suggests an exogenic origin delivery from space rather than internal production. Yet even if Ceres' organics came from elsewhere, their presence tells us something profound. Organic materials were common in the early solar system, delivered across vast distances by impacting bodies. And Ceres itself may have once possessed conditions suitable for complex chemistry. In August 2024, researchers published evidence that ancient Ceres had all 3 requirements for habitability: water, organic materials, and a chemical energy source. Between 2.5 and 4 billion years ago, radioactive decay in Ceres' rocky core reached peak temperatures exceeding 550 Kelvin, hot enough to trigger hydrothermal activity. Hot water carrying dissolved gases like carbon dioxide, hydrogen, and methane percolated from the core into the overlying ocean, providing chemical energy that microorganisms might have used for metabolism. For perhaps hundreds of millions of years, Ceres may have been habitable. Did life ever emerge on Ceres? We don't know. Modern Ceres is almost certainly uninhabitable, too cold, with insufficient ongoing heat to maintain the chemistry required for life. The radioactive elements that once powered its interior have largely decayed. The ocean has mostly frozen. Yet the possibility that Ceres was once habitable opens a staggering implication. If a body as small as Ceres could achieve habitable conditions, then similar-sized objects throughout the early solar system might have also hosted habitable environments. There may have been hundreds or thousands of small ocean worlds in the first billion years after the solar system formed. Most were destroyed or ejected, their stories lost forever. But Ceres survived, and in its ancient interior, written in frozen chemistry, may be a record of habitable conditions we're only beginning to read. Ceres occasionally releases a transient water vapor exosphere, not a true atmosphere, but a thin envelope of water molecules with a lifetime of only 7 hours before they're lost to space or redeposited on the surface. The Herschel Space Observatory first detected these localized releases in 2014, confirmed later by Dawn. Each active source releases about 3 kilograms of water per second, equivalent to 10 to the 26th water molecules. The source is likely sublimation. Ice exposed in certain areas absorbs sunlight, heat slightly above the frost point, and releases water vapor directly from solid ice to gas without passing through a liquid phase. This isn't proof of ongoing volcanic activity, but it does demonstrate that Ceres remains dynamic, still releasing water from its interior or near-surface reservoirs. Even frozen worlds can breathe. Dawn's mission concluded in October 2018 when the spacecraft finally exhausted its hydrazine fuel, ending its ability to point its instruments and communicate with Earth. Mission controllers deliberately left Dawn in a long-term stable orbit around Ceres, where it will remain for at least 2 decades, possibly centuries. The spacecraft itself has become an artifact, a monument to the mission that transformed our understanding of the largest asteroid. Dawn mapped Ceres in extraordinary detail, captured over 68,000 images, and detected neutrons from cosmic rays interacting with the surface, confirming the presence of subsurface ice even in the absence of direct visual evidence. The mission demonstrated that dwarf planets are not simple objects, but complex worlds with their own geology, hydrology, and evolutionary histories. What? Dawn revealed at Ceres echoes discoveries made elsewhere in the solar system. Ocean worlds are far more common than we imagined. Jupiter's moon. Europa almost certainly has a global subsurface ocean. Saturn's moon. Even Pluto, 3 billion miles from the Sun, may harbor a subsurface ocean. The pattern is clear. Liquid water exists throughout the solar system, hidden beneath ice shells, preserved by salts that lower freezing points, warmed by radioactive decay or tidal flexing. Ceres fits this pattern perfectly. It's an ocean world in miniature, demonstrating that even asteroids' bodies we once considered dead rocks can harbor complex chemistries and dynamic processes. The line between planets and asteroids is blurrier than we thought. Ceres' discoveries raise questions that extend far beyond one dwarf planet. If Ceres was habitable billions of years ago, and if similar conditions existed on hundreds of other icy bodies, what does that mean for the origin of life in our solar system? Could life have emerged independently on multiple small bodies, then gone extinct as they cooled? Could microorganisms have survived in isolated subsurface reservoirs, waiting in dormancy for billions of years? Or could life have originated on one body and spread to others through impacts that ejected material into space, a process called panspermia? These questions are no longer merely theoretical. They're empirical questions that future missions might answer by returning samples from Ceres, drilling through its ice, and analyzing its subsurface fluids directly. For now, Ceres guards its deepest secrets. The subsurface brine reservoir remains inaccessible, 40 kilometers beneath an ice shell we cannot yet penetrate. The ancient hydrothermal environments where habitability may have emerged are frozen and silent. The organic materials scattered across the surface offer only tantalizing hints of complex chemistry. But we've learned enough to know that Ceres is not a simple asteroid. It's a world, a dwarf planet with a history as complex and profound as any in the solar system. And in its frozen depths may lie answers to questions we've asked since we first looked up at the stars and wondered, are we alone? Why does the asteroid belt exist at all? In the early solar system, planet formation should have proceeded smoothly in the region between Mars and Jupiter. Dust particles collided and stuck together, building larger aggregates through billions of gentle collisions. Pebbles became boulders, boulders became kilometer-sized planetesimals. The building blocks of planets. Everywhere else in the solar system, this process continued until full planets formed. Between Mars and Jupiter, it stopped. The planetesimals that would have assembled into a world roughly the size of Earth instead remained scattered, broken, reduced to less than 4% of the Moon's mass. What interrupted the process? What prevented a fifth rocky planet from forming? The answer orbits beyond the asteroid belt, a gravitational tyrant whose influence reshaped the entire solar system. Jupiter formed early and formed fast, accumulating enough mass that its gravitational influence dominated the outer solar system. As the giant planet grew, it created orbital resonances, specific distances where an asteroid's orbital period forms a simple mathematical ratio with Jupiter's period. At these resonance locations, asteroids experience repeated gravitational tugs from Jupiter at the same point in their orbits. Over time, these perturbations accumulate, pumping up the asteroid's velocities and orbital eccentricities. Their orbits become more elliptical, more tilted, more energetic. Collisions that should have resulted in gentle sticking and growth instead become violent, shattering impacts. The transition from accretion to fragmentation prevents planet formation. Jupiter didn't directly destroy a planet between Mars and its orbit. It prevented one from ever forming in the first place. The Kirkwood gaps, discovered in 1866 by astronomer Daniel Kirkwood, reveal these resonance zones as depleted regions where few asteroids survive. At the 3-to-1 resonance, located at 2.5 astronomical units, an asteroid would complete 3 orbits for every 1 Jupiter orbit. At the 2-to-1 resonance at 3.27 astronomical units, it would orbit twice per Jupiter orbit. These locations are gravitational no-man's lands. Any asteroid that wanders into a Kirkwood gap has its orbit perturbed over time until it's ejected from the belt entirely, perhaps falling into the Sun, perhaps being flung into the outer solar system, perhaps colliding with a planet. The gaps exist because Jupiter has been steadily clearing them for billions of years. They're scars in the belt's structure, permanent testimony to Jupiter's influence. But Jupiter did something even more dramatic than preventing planet formation. According to the Grand Tack hypothesis, proposed in 2011, Jupiter didn't always orbit at its current distance of 5.2 astronomical units. The giant planet initially formed around 3.5 astronomical units from the Sun, then migrated inward through interactions with the gaseous protoplanetary disk. Jupiter moved sunward like a ship tacking against the wind, a grand tack reaching as close as 1.5 astronomical units. This brought Jupiter into what is now the inner asteroid belt, perhaps even encroaching on Mars's current orbit. Then, when Saturn formed and became locked in orbital resonance with Jupiter, the two giants reversed course and migrated back outward. This journey fundamentally restructured the asteroid belt and reshaped the inner solar system. As Jupiter swept inward, it gravitationally scattered nearly everything in its path. The original asteroid belt, which may have contained an Earth mass worth of material, was almost completely emptied. Computer simulations suggest that 99.9% of the original mass was lost in the first 100 million years. Some material fell into the Sun. Some was ejected to the outer solar system or beyond. Some collided with the inner planets during a period of intense bombardment. During the outward migration, Jupiter's gravity scattered material back into the belt region, but only a tiny fraction of what originally existed. The asteroids we see today are survivors, a remnant population, refugees that happened to end up in relatively stable orbits after the migration ended. We're looking at less than 0.1% of the original belt. The Grand Tack elegantly explains several solar system mysteries simultaneously. First, the compositional gradient, S-type silicate asteroids dominating the inner belt, originated from warmer regions inside Jupiter's original orbit, while C-type carbonaceous asteroids in the outer belt came from colder regions beyond Jupiter. The migration mixed these populations. Second, Mars's puzzling small size. Jupiter's presence in the inner solar system scattered away material that Mars would otherwise have accreted. Mars isn't small by chance. It's small because Jupiter starved it of building material. Third, the wide range of asteroid orbital inclinations and eccentricities. These result from violent dynamical excitation during Jupiter's migration. The belt's structure preserves a memory of Jupiter's journey through the inner solar system billions of years ago. The asteroid belt continues evolving even today. A 2025 study shows the belt is losing approximately 0.0088% of its collision, participating mass annually through ongoing impacts and gravitational ejections. The belt was roughly 50% more massive 3.5 billion years ago. Material lost from the belt includes bodies ejected onto planet, crossing orbits maintaining the population of near-Earth asteroids that occasionally threaten our world. Every few decades or centuries, an asteroid is nudged by a distant Jupiter resonance, by the Yarkovsky effect, subtle thermal radiation pressure, or by a collision, and begins a long, chaotic journey inward. Some will eventually impact planets. Some will be ejected from the solar system entirely. The belt is slowly bleeding mass, a process that will continue for billions of years until, eventually, only the most stable asteroids remain. Despite Jupiter's destructive influence, we should perhaps be grateful. If Jupiter hadn't prevented a planet from forming in the belt region, we'd have 5 rocky planets instead of 4, and the inner solar system's dynamics might be completely different. Mars might be much larger, potentially interfering with Earth's orbit. The asteroid bombardment of the inner planets might have been more or less intense, changing the delivery of water and organics to early Earth. Life's emergence might have been delayed, prevented, or accelerated. Jupiter's influence wasn't purely destructive, it was selective, reshaping the solar system in ways that ultimately led to conditions suitable for our existence. We are, in a sense, children of Jupiter's grand tack, products of a migration that occurred 4.5 billion years ago. Why do asteroids matter? Why send spacecraft millions of miles to study what seems like cosmic rubble? The answer lies in what asteroids have preserved, an unaltered record of the solar system's earliest days. Unlike Earth, Venus, and Mars, which melted completely, differentiated into core, mantle, and crust, and continue active geology that recycles and erases their surfaces, most asteroids experienced only brief heating 4.5 billion years ago. That heating ended by about 4.5 billion years ago, leaving them in geological stasis for the subsequent billions of years. Asteroids are archives. Well, they're libraries. They're time capsules sealed shortly after the solar system's birth and opened only now by spacecraft sent to read what's been preserved inside. The most primitive meteorites, the chondrites, contain millimeter-sized spheres called chondrules. These are droplets of once molten rock that formed in the protoplanetary disk, perhaps flash-heated by shockwaves or lightning-like electrical discharges, then rapidly cooled and solidified. Chondrules haven't melted since they first formed. They preserve the solar system's chemical composition minus the volatile gases that escaped. When you hold a chondrite meteorite in your hand and see these tiny spheres embedded in the rock, you're looking at material older than the planets. Some meteorites contain refractory inclusions, minerals that condense only at extremely high temperatures. These are the oldest dated materials in the solar system, 4.567 billion years old. That's time 0. That's when the solar system clock started ticking. Some meteorites contain pre-solar grains, literally stardust from ancient stars that died before our solar system formed. These grains are identified by their distinctive isotopic compositions, which differ from solar system material. They're the ashes of long-dead stars incorporated into the cloud of gas and dust from which our solar system condensed. When you analyze a pre-solar grain, you're studying a star that died perhaps billions of years before the sun ignited. That star's nuclear furnace created these exotic isotopes, then expelled them in a supernova or stellar wind. The grains drifted through interstellar space, eventually finding their way into the solar nebula, surviving the sun's birth, and being incorporated into asteroids that ultimately delivered them to Earth. We can touch materials older than the sun. That's astounding. Of the 50,000 meteorites found on Earth, 99.8% originated in the asteroid belt. This provides ground truth for understanding asteroid compositions. We can compare spacecraft observations with laboratory analysis of meteorites, confirming our interpretations and building a comprehensive understanding of what asteroids are made of. But there's a limitation. Meteorites are biased samples. They represent only the materials strong enough to survive atmospheric entry and impact with Earth's surface. The most fragile, volatile-rich, primitive materials rarely survive the journey intact. That's why sample return missions are invaluable. By carefully collecting material from an asteroid's surface and returning it sealed in a pristine container, we can study materials that would never survive as natural meteorites. We can examine the asteroid belt's most fragile secrets. Isotopic analysis reveals profound secrets. Scientists have discovered that meteorites divide into 2 distinct groups based on differences in titanium, chromium, oxygen, and other element isotopes. One group, The non-carbonaceous or NC meteorites represent material from the inner solar system. The other carbonaceous or CC meteorites come from the outer solar system beyond Jupiter's orbit. These groups remained spatially separated for 1 to 4 million years after solar system formation, with very little mixing. What kept them apart? Jupiter. The rapidly forming giant planet created a pressure barrier in the protoplanetary disk, inhibiting material exchange between inner and outer regions. This isotopic dichotomy provides independent evidence supporting Jupiter's early formation and its role in structuring the solar system. The chemistry of asteroids records Jupiter's ancient influence. Asteroids record the protoplanetary disk's temperature gradient with exquisite precision. C-type asteroids preserve clay minerals and hydrated silicates which can form only below about 400 degrees Celsius. S-type asteroids contain anhydrous minerals that formed at higher temperatures. M-type metallic asteroids may represent cores that formed through differentiation, requiring temperatures above 1000 degrees. By mapping where these different types exist today and accounting for Jupiter's migration, we can reconstruct the temperature zones of the ancient disk. We can determine that the snow line, where water ice could condense, existed around 2.7 astronomical units. We can trace how temperature decreased with distance from the Sun, creating fundamentally different materials at different locations. The belt is a thermometer, still reading the temperature of a disk that vanished 4 billion years ago. The high-temperature materials in carbonaceous asteroids demonstrate that the early solar system was far more dynamic than simple models suggested. Bennu and Ryugu contain refractory inclusions, materials that formed near the Sun at temperatures exceeding 1,300 Kelvin, mixed with ices and organic compounds that could form only in the cold outer solar system. How did these extreme temperature materials come to exist side by side in the same asteroid? Radial transport. The protoplanetary disk was turbulent, with spiral density waves, magnetic fields, and gas flows creating mixing currents that transported material across vast distances. Rocks that formed near the Sun were carried outward. Ices from the outer regions were scattered inward. The early solar system wasn't orderly, it was chaotic, churning, actively redistributing its ingredients across the entire disk. This mixing has profound implications for understanding Earth's formation. If materials from across the entire protoplanetary disk were redistributed and mixed, then Earth likely incorporated elements from both inner and outer solar system regions. The water in Earth's oceans may have come from carbonaceous asteroids originally formed beyond Jupiter. The organic molecules that enabled life's emergence may have been delivered by comets from the outer solar system. We are not purely creatures of the inner solar system. We're composites, assembled from materials that originated across a vast range of distances and temperatures. The asteroid belt, by preserving unmixed samples from different regions, allows us to deconstruct this cosmic recipe and understand where Earth's ingredients originated. Reading the belt is reading Earth's birth certificate. On September 24, 2023, a small capsule streaked through Earth's atmosphere at 27,000 miles per hour, its heat shield glowing white-hot from atmospheric friction. Parachutes deployed, slowing the descent, and the capsule touched down gently in the Utah desert. Inside, sealed in a pristine container, was treasure beyond measure, 121.6 grams of material from asteroid Bennu. This was the culmination of NASA's OSIRIS-REx mission, 7 years of travel and careful work to reach Bennu, study it, touch it briefly to collect samples, and return them safely to Earth. These samples would prove to be the most significant materials yet returned from beyond the Moon, rewriting our understanding of organic molecules in the early solar system. When scientists opened the sample container, they faced an unexpected challenge. The material was so rich in carbon and organics that it had stuck to the container's lid, complicating the opening procedure. This wasn't contamination. This was Bennu's true nature revealing itself. The asteroid is dominated by clay minerals, particularly serpentine, a hydrated phyllosilicate that forms when water interacts with rocky minerals. About 80% of Bennu's minerals contain water in their crystal structures. The sample's appearance was darker than expected, almost black, with a consistency somewhere between powder and sticky clay. This is what 4.6 billion-year-old material from the outer solar system looks like: dark, carbon-rich, water-bearing, and extraordinarily fragile. The June 2024 preliminary analysis confirmed what scientists hoped but couldn't prove until they had pristine samples. Bennu contains all 5 nucleobases that make up DNA and RNA: adenine, thymine, cytosine, guanine, and uracil. The fundamental information. Storage molecules of life all exist in this asteroid material. The sample also contains 14 of the 20 amino acids used by life on Earth to construct proteins. There's abundant ammonia, critical for biological chemistry. There's formaldehyde, which reacts with ammonia to form complex organic molecules. The January 2025 announcement represented perhaps the most significant astrobiology discovery in decades, definitive proof that life's chemical building blocks were widespread in the early solar system, delivered to Earth by asteroid impacts. Bennu samples contain pre-solar grains, stardust older than the Sun, identified by their exotic isotopic signatures that differ from solar system material. As University of Arizona scientist Jessica Barnes explained, these are pieces of stardust from other stars that are long dead, incorporated into the cloud of gas and dust from which our solar system formed. The samples also revealed high-temperature materials that formed near the Sun mixed intimately with icy materials from the cold outer solar system, confirming the dynamic, turbulent nature of the early protoplanetary disk. Bennu is a mongrel, a mixture, an asteroid assembled from materials that originated across vast distances. Its composition tells a story of chaos and mixing, of materials redistributed across the entire solar system in its violent youth. Salt minerals in the samples, halite and sylvite, indicate ancient sodium-rich brines existed on Bennu's parent body. This larger asteroid, perhaps tens of kilometers across, accreted substantial ice from the outer solar system. Internal radioactive heating melted that ice, creating liquid water that percolated through the rocky interior, dissolving minerals and creating brines. These fluids altered the original minerals, creating the clay-rich material we see in Bennu today. Eventually, the parent body was catastrophically disrupted by a collision. Bennu is a fragment of that ancient, water-rich world, a chip off an old block that once harbored liquid water and organic chemistry. The parent body is gone, destroyed billions of years ago. But Bennu survived, carrying evidence of its parent's wet history. Why are sample return missions so valuable compared to studying meteorites that fall naturally? Contamination control. From the moment a meteorite enters Earth's atmosphere, it begins contaminating. Atmospheric friction heats the surface, vaporizing volatiles. Impact with Earth's surface adds terrestrial materials. Rain, soil bacteria, fungi, and organic molecules from Earth's environment quickly invade the rock's pores and cracks. Within weeks or months, distinguishing extraterrestrial organics from terrestrial contamination becomes nearly impossible. A November 2024 study showed that despite stringent controls, terrestrial microorganisms rapidly colonized the Ryugu samples returned by Japan's Hayabusa 2 mission. Preventing contamination is extraordinarily difficult. But by collecting samples in a sealed container in space and keeping them sealed until opened in a clean room, we can analyze materials in near pristine condition, revealing subtleties that would be obliterated in any natural meteorite. OSIRIS-REx, now renamed OSIRIS-APEX, didn't end its mission with the sample return. The spacecraft continues onward toward asteroid Apophis, arriving April 13, 2029 for an 18-month study. Apophis is particularly interesting because on that date it will pass just 30,600 kilometers from Earth, inside the orbits of geostationary satellites. Earth's tidal forces during this close encounter may trigger surface changes, landslides, seismic shaking, refreshing of the surface as buried materials are exposed. OSIRIS. The spacecraft that taught us about Bennu will now teach us about a different class of asteroid under completely different circumstances. Japan's Hayabusa 2 mission, which returned samples from carbonaceous asteroid Ryugu in December 2020, continues its extended mission toward asteroid 1998, KY26, arriving in 2031. The Ryugu samples revealed organic molecules likely formed around water, confirming similar chemistry to what OSIRIS-REx found at Bennu. These parallel discoveries from two independent missions studying two different asteroids confirm a crucial fact. Complex organic chemistry was common in the early solar system, not rare or localized. Carbonaceous asteroids throughout the belt likely harbor similar materials. The building blocks of life weren't special or unusual. They were ubiquitous, scattered across the solar system, waiting to be delivered to any planet with suitable conditions. Life's emergence required only that these ingredients find their way to a warm, wet world. Two extraordinary missions currently make their way through the solar system, each targeting unique populations of asteroids we've never properly explored. NASA's Lucy mission, launched in October 2021, is on a 12-year odyssey to visit 11 asteroids, the most ambitious asteroid tour ever attempted. Its primary targets are Jupiter's Trojan asteroids, ancient bodies trapped at Jupiter's L4 and L5, Lagrange points, gravitational islands of stability where objects orbit in sync with Jupiter itself. These Trojans are fossils of planet formation, primordial materials from the outer solar system preserved for 4.6 billion years. They may represent the building blocks of the outer planets, samples of the material that assembled Jupiter, Saturn, Uranus, and Neptune. No spacecraft has ever visited the Trojans. Lucy will be the first. Lucy's journey includes main belt encounters as rehearsals for the Trojan visits. On April 20th, 2025, Lucy flew past asteroid Donald Johanson, revealing a surprising contact binary. A barbell-shaped object about 8 kilometers long formed from two bodies stuck together. This echoes discoveries at other asteroids. Many small bodies are contact binaries or rubble piles, aggregations assembled from fragments after collisions rather than single coherent rocks. The encounter served as a critical test of Lucy's instruments and navigation systems. Everything worked perfectly. The spacecraft is ready for its primary mission, beginning in August 2027 when it reaches Eurybates, a large carbonaceous Trojan with a small moon named Cater. From there, Lucy will visit 6 more Trojans over the following 6 years. The Trojan asteroids hold special significance because they've spent 4.6 billion years in cold storage. Unlike main belt asteroids, which occasionally collide and have undergone billions of years of slow evolution, the Trojans remain relatively pristine. Their orbits are stable over geological timescales. They experience minimal heating from the sun given their distance. They've avoided most of the dynamical stirring that affected the main belt. If you want to understand what the outer solar system's building materials look like immediately after planet formation, the Trojans are your best bet. They're time capsules from a region of the disk that produced the giant planets. Lucy's observations will reveal whether the Trojans resemble the asteroids we know, or whether they're fundamentally different. Populations telling us about material from farther out in the protoplanetary disk. Lucy's most extraordinary target comes in March 2033, the binary Trojan system, Patroclus, Menoetius. These are two roughly equal-sized objects, each about 100 kilometers across, orbiting their common center of mass every 103 hours. Binary systems are natural laboratories for studying gravitational interactions, tidal effects, and formation mechanisms. Did Patroclus and Menoetius form together as twins? Or did they meet later and become gravitationally captured? Are they contact binaries that separated, or independent bodies that never touched? Their matching sizes, colors, and compositions suggest they originated from the same parent body, perhaps split apart during a collision. Lucy will observe both objects, measure their masses and densities, map their surfaces, and determine how binary asteroids form in the outer solar system. Meanwhile, NASA's Psyche mission travels toward perhaps the strangest asteroid in the belt, 16 Psyche, a metallic world that may be an exposed planetary core. Launched October 13, 2023 on a SpaceX Falcon Heavy, Psyche encountered a propulsion system issue in April 2025 when tank pressure dropped unexpectedly. Engineers successfully switched to a backup propellant line and restored full operations by June, demonstrating the value of redundant systems on deep space missions. The spacecraft now cruises beyond Mars orbit using revolutionary Hall effect ion thrusters, generating just 92 millinewtons of thrust, about the weight of a AA battery, but operating continuously for years, gradually accumulating velocity through persistence rather than power. Psyche will arrive at its target in August 2029, Asteroid. Psyche itself is an enigma. At 220 kilometers diameter and composed primarily of nickel-iron metal, it likely represents the core of a shattered protoplanet. Imagine a world forming 4.5 billion years ago, growing large enough that its interior melts and differentiates. Heavy iron and nickel sink to the center, forming a metallic core. Lighter silicate rocks float upward, creating a mantle and crust. Then catastrophe strikes, a massive collision so violent it strips away all the rocky exterior, leaving only the metallic heart exposed to space. Ooh. That's Psyche. It may contain 30 to 60% metal by volume, possibly up to 95% in some regions. If we could somehow transport Psyche to Earth's orbit and mine it, the metal content might be worth $10 quintillion. Of course, the logistics and economics make this pure fantasy, but it illustrates the extraordinary composition. Psyche will conduct a 26-month orbital study concluding in October 2031, mapping the asteroid's surface, measuring its magnetic field, if any remains from its core-forming days, and determining its composition precisely. The mission carries no sample return capability. Instead, it relies on remote sensing, multispectral imaging, gamma-ray and neutron spectroscopy, and magnetometry. One key question: is Psyche truly a planetary core fragment, or is it a primordial metal-rich object that never fully differentiated? Recent observations suggest Psyche's surface may contain more silicate minerals than expected for a pure core, complicating the interpretation. The mission will resolve this mystery and reveal whether we're looking at a destroyed planet's remains or a unique primordial object. Psyche achieved another milestone beyond its asteroid science, successful demonstration of deep space, optical communications technology in December 2023. The spacecraft transmitted a CAT video from 31 million kilometers away at 267 megabits per second, comparable to terrestrial broadband speeds. During testing, Psyche downloaded 1.3 terabits of data, equaling the entire data volume from NASA's Magellan Venus mission that operated from 1990 to 1994. This technology will revolutionize deep space communications, enabling orders of magnitude more data returned from future missions. The asteroid belt is becoming not just a destination for study, but a proving ground for technologies that will enable exploration throughout the solar system and beyond. These missions transform asteroids from remote targets into accessible worlds. Most asteroids remain in the belt, minding their own business, orbiting peacefully for billions of years. But occasionally one gets nudged by a collision, by a resonance with Jupiter, by the subtle Yarkovsky effect where absorbed sunlight creates tiny thrust. Its orbit changes. It's me. It begins wandering. Eventually, it crosses Earth's path, becoming what we call a near-Earth asteroid. There are over 34,000 known near-Earth asteroids today, with more discovered every week. Most pose no threat. They'll pass harmlessly by Earth for millions of years. But occasionally, rarely, one comes too close. In December 2024, humanity faced its first real test of planetary defense coordination when asteroid 2024 YR4 was discovered with up to a 3.1% chance of impacting Earth on December 22, 2032. This triggered activation of the United Nations International Asteroid Warning Network. 2024, YR4 reached level 3 on the Torino Impact Hazard Scale, the highest rating since Asteroid. Apophis reached level 4 in 2004. Initial estimates suggested an asteroid between 40 and 90 meters in diameter, roughly the height of a 15-story building. The James Webb Space Telescope targeted the asteroid in March 2025, using its superior infrared capabilities to refine the size estimate to 53 to 67 meters with S-type stony composition. This was crucial information. A rocky asteroid of this size impacting land would create a crater over a kilometer wide and release energy equivalent to dozens of megatons of TNT. If it hit an ocean, it could trigger a devastating tsunami. For several months, planetary defense teams worldwide developed contingency plans, calculating potential deflection missions. By February 2025, additional observations essentially ruled out Earth impact. The probability dropped to 0.004%. However, while a lunar impact wouldn't threaten Earth directly or significantly alter the Moon's orbit, it could create a debris field threatening satellites and spacecraft in Earth orbit. The asteroid will remain too distant for accurate observation until it returns in 2028, when telescopes can refine its orbit with higher precision. The incident demonstrated both the strengths and gaps in our planetary defense capabilities. We can detect threats, but asteroids approaching from the day side from the direction of the Sun remain difficult to spot until they're already very close. This blind spot became tragically clear on February 15, 2013, when a 20-meter asteroid exploded over Chelyabinsk, Russia, without warning. The object approached from the direction of the Sun, rendering it nearly invisible to ground-based telescopes. It entered Earth's atmosphere at 43,000 miles per hour, releasing energy equivalent to 500 kilotons of TNT, about 30 times the Hiroshima bomb's yield. The shockwave shattered windows across 6 cities, injuring over 1,500 people. Most injuries came from flying glass when the sonic boom arrived, catching people standing at windows watching the brilliant fireball streak across the morning sky. Chelyabinsk was a wake-up call. Even relatively small asteroids can cause significant damage, and we can't see everything coming. Humanity's first practical demonstration of planetary defense occurred on September 26, 2022, when NASA's DART spacecraft deliberately crashed into Dimorphos, a 160-meter moonlet orbiting the larger asteroid Didymos. The collision wasn't designed to destroy Dimorphos, but to nudge it, changing its orbital period around Didymos by a small but measurable amount. The impact succeeded beyond expectations. Dimorphos's 11-hour 55-minute orbital period decreased by 33 minutes. The kinetic impact also physically deformed Dimorphos, changing its shape from a relatively round body to a more elongated, somewhat flattened form. The asteroid proved to be a rubble pile, a loose aggregate of fragments held together only by weak gravity, making the deflection more efficient than if it had been solid rock. The European Space Agency's Hera mission, launched October 7, 2024, will follow up on DART's success. After a Mars gravity assist in March 2025, Hera will reach the Didymos system in December 2026 for 6 months of detailed study. The mission will measure the exact size and morphology of DART's impact crater, determine how much momentum was transferred to Dimorphos, and conduct the first comprehensive survey of a binary asteroid system. Hera will deploy 2 CubeSats, Juventas, carrying a radar to probe Dimorphos's interior structure, and Milani for detailed spectral analysis of surface composition. Together, DART and Hera transform a successful demonstration into validated, repeatable planetary defense technique. We now know kinetic impactors work. The question becomes, how much advance warning do we need? For 2024 YR4, researchers calculated deflection options if the threat proves real. A kinetic impactor mission, similar to DART, could launch during a window from April 2030 to April 2032, with several years of flight time to intercept. Alternative calculations show nuclear disruption remains feasible for asteroids in this size range, using a 1 megaton device to fragment the asteroid into smaller pieces that would mostly burn up in Earth's atmosphere. However, kinetic deflection is strongly preferred whenever possible. It's simpler, safer, requires no nuclear weapons in space, and doesn't risk creating multiple dangerous fragments. The key requirement is time. Given enough advance warning, ideally decades, we can deflect almost any asteroid. Without warning, our options become limited and riskier. The asteroid belt continues to slowly bleed material into the inner solar system, maintaining the population of near-Earth asteroids through a steady trickle of objects nudged onto planet-crossing orbits. Every few decades or centuries, Jupiter's resonances, the Yarkovsky effect, or a collision sends another asteroid inward. Most will eventually impact the Sun or be ejected from the solar system. Some will hit planets. Earth receives these visitors regularly. Fortunately, most are tiny, burning up harmlessly in the atmosphere as meteors. But the larger ones, the ones that could cause regional or global catastrophe, require vigilance. The asteroid belt is not just a scientific treasure trove or a window into the past. It's also the source of potential threats we must monitor and, if necessary, deflect. Understanding asteroids isn't just about satisfying curiosity. It's about ensuring our survival. Let's bring this journey home. We've traveled through the vast emptiness of the asteroid belt, visited ancient protoplanets and ocean worlds, examined pristine samples containing life's building blocks, and watched humanity take its first steps in planetary defense. But there's one final connection to make, one final truth that transforms the asteroid belt from distant curiosity into intimate reality. The atoms that make up your body, every single one, were forged in stellar furnaces billions of years ago, scattered into space by dying stars, incorporated into the molecular cloud that collapsed to form our solar system, locked into asteroids and planets during formation, and eventually delivered to Earth. You are not separate from the asteroid belt. You are made of the same materials. You are Stardust, given consciousness and the ability to contemplate your own origins. The iron in your blood, the hemoglobin molecules that carry oxygen to every cell in your body, was created inside a dying star through nuclear fusion. When that star exploded as a supernova, it scattered that iron across interstellar space. The calcium in your bones was also forged in stellar cores and distributed by supernovae. The carbon in your DNA, the nitrogen in your proteins, the oxygen you breathe, all created by stars, all incorporated into the protoplanetary disk, all locked into asteroids 4.6 billion years ago. Asteroids delivered these elements to Earth through impacts during the solar system's first few 100 million years. The materials that built our planet, that enabled life's emergence, came from the asteroid belt and beyond. Looking at asteroids isn't looking at something alien. It's looking at our extended family. Earth's water, the oceans, the ice caps, the water in every living cell, likely came primarily from asteroids. Carbonaceous asteroids contain up to 20% water by mass, locked in hydrated minerals and ice. During Earth's formation and the subsequent late heavy bombardment about 4 billion years ago, countless water-rich asteroids impacted our planet, delivering enough water to fill the oceans. Recent isotopic analysis of Bennu samples confirms that carbonaceous asteroids match Earth's water composition closely, supporting this delivery hypothesis. Every time you drink water, you're consuming material that rode asteroids across hundreds of millions of miles of space, survived violent impacts, and has circulated through Earth's hydrological cycle for billions of years. That water has been inside dinosaurs, flowing through ancient rivers, frozen in ice ages, and now flows through you, the organic molecules necessary for life's emergence. Amino acids, nucleobases, lipids, sugars were also delivered by asteroids and comets. The Bennu samples prove this beyond doubt. Complex organic chemistry occurred throughout the early solar system, not just on Earth. These molecules didn't spontaneously appear on our planet. They arrived from space, survived atmospheric entry and impact, accumulated in warm ponds and deep-sea hydrothermal vents, and eventually assembled into the first self-replicating systems we call life. In a very real sense, life on Earth is not purely terrestrial. It's cosmic. We are the universe's attempt to understand itself, built from materials created in stars, delivered by asteroids, assembled through chemistry on a rocky planet, and now evolved enough to send spacecraft back to those same asteroids to study our origins. The asteroid belt story is ultimately our story. When Jupiter's migration stirred the belt and ejected 99.9% of its mass, some of that material fell inward and built Earth. When asteroids underwent aqueous alteration on their parent bodies, creating clay minerals and organics, they were processing materials that would someday enable consciousness. When Ceres developed a subsurface ocean and potentially habitable conditions, it was demonstrating that the requirements for life are common, not rare. The belt isn't separate from Earth's history. It's woven into every chapter. Understanding the belt means understanding where Earth's building materials originated, how they were processed, and why our planet ended up with the specific composition that made life possible. The belt is Earth's extended family photo album, showing us our ancestors and relatives. Recent discoveries have accelerated our understanding at an incredible pace. The OSIRIS-REx and Hayabusa 2 sample returns confirmed organic abundances far exceeding what meteorite studies suggested. The Dawn mission revealed Ceres as an active ocean world when we expected a dead rock. The DART impact demonstrated practical planetary defense. The Lucy and Psyche missions now en route will reveal populations of asteroids we've never properly explored. The Gaia Space Telescope discovered that binary asteroids are far more common than we thought. Every new mission rewrites textbooks. Every sample return opens new questions. We're living through a golden age of asteroid science, where our understanding expands faster than at any previous time in history. And we've barely scratched the surface. The belt holds secrets we haven't even imagined yet. What's next for asteroid exploration? NASA's NEO Surveyor will become the first space telescope specifically designed to hunt potentially hazardous asteroids, particularly those approaching from the Sun's direction where ground-based telescopes struggle. Future sample return missions may target M-type metallic asteroids, Trojan asteroids, or even return samples from Ceres' bright spots. Proposals exist for orbiter missions to Pallas, flyby missions to high-inclination asteroids, and even concepts for drilling through Ceres' ice to sample its subsurface brine. Each mission reveals the unexpected. Each discovery raises new questions. The asteroid belt is becoming less of a remote region to observe through telescopes and more of a destination to visit, touch, sample, and eventually perhaps even inhabit. These are worlds we can reach within years, not decades. They're accessible in ways that planets beyond Mars are not. As we conclude this journey, consider what the asteroid belt represents. It's a graveyard of a planet that never formed, yet that graveyard preserves more information about our cosmic origins than any thriving world could. It's a place of profound emptiness, yet that emptiness allowed asteroids to remain unchanged for billions of years. It's a collection of dead rocks, yet those rocks harbor evidence of ancient oceans, complex chemistry, and possibly even past habitability. It's millions of miles away, yet it's also here, within us, part of our very atoms and molecules. The asteroid belt is not other. It's self. It's self. And in studying these ancient worlds, we're not looking outward at the cosmos. We're looking inward at the materials and processes that created us. The belt isn't just out there in space. It's also in here, in us, connecting our existence to the stars. Our drift through the asteroid belt is complete. We've witnessed the vast emptiness that defies Hollywood's imagination, touched ancient samples containing life's building blocks, explored dwarf planets harboring hidden oceans, and traced the cosmic materials that built our world and our bodies. The asteroids remain out there, tumbling silently through space, keeping their vigil over secrets 4.6 billion years old. But they're no longer strangers. They're family. They're family. As you return to your world, carry this knowledge. You are made of materials forged in stellar furnaces, delivered by asteroids, assembled by chemistry into the miraculous complexity of conscious life. You are the universe's way of knowing itself. What will you do with that knowledge? How does it change your perspective to know that you're not separate from the cosmos, but intimately woven into its fabric? Rest now. Dream of ancient worlds, and know that the stardust that built you connects you to everything that ever was and everything that ever will be.